Hello everyone. Today we are going to see the knuckle joint or the overall procedure of design for this knuckle joint. So first we will see what is the knuckle joint and where we use, what are the applications of this knuckle joint. Knuckle joint we normally use to connect the two rods whose axes are either coinciding or they intersect and lie in one plane. And the knuckle joint that we use to transmit the actual tensile force. And here even some limited angular movement between the joints, that is also somewhat permitted. For this purpose we are using the knuckle joint. So this is the knuckle joint, the front view and the top view. Three major parts are there in this. That is the one, the fork end. So this is the fork end and this is the eye end and the pin. Here are the few dimensions that we will see one by one. Capital D we are using, that capital D is what diameter of this rod. The diameter of either it is the fork end or at the eye end. So this diameter, that we can say capital D. D1 is enlarged diameter of each rod. So this portion, this is the enlarged diameter up to this. So this diameter, it is the enlarged diameter. Here in the top view you can see this is the D1, both of that, the fork and the eye end. So it is enlarged diameter. Then small d it is there, here it is the diameter of the knuckle pin. So this is the pin which we are using to connect the two ends, that is the fork end and the eye end. So its diameter is small d. Then small d to the base O, DO, we can say outside diameter of the fork end. So this is the fork and its end, this is the fork end. So this outside diameter, here you can see from this end to this, it is the DO. A, small a, it is the thickness of the fork, right? So each eye, so this is what the thickness of the fork end, right? So this is the fork end and its thickness, it is A, and B is thickness of this the eye end, here that is the small b we can say. Then D1 is the diameter of this pin head, whatever the diameter D, that is the pin, its head, here it is its head, that we are denoting it by the D1. X is what the distance of the center of the fork radius and this end. So here was the center of this arc, it is having its center from this end to this, the eye end, its distance, that we are denoting it by the X. Now where we can use this knuckle joint? The first one, joint between the tie bars of the roof truss, that we will see in figure, next slide. Then joint between the links of the suspension bridge, even in case of the two-wheeler, whatever the suspensions we are using, in that also we are using this knuckle joint. Then the joint in the valve mechanism of the reciprocating engine. Then the fulcrum of the lever. Then joint between the links of the bicycle chain which we are using. So now we will see the first one we had seen, the tie rod joint in the roof truss. So this is the roof and this is the truss member is there, and here we are using the joint. Even if I enlarge, then you will come to know here it is the joint. So this is the fork end, eye end, and here in between the cotter pin which we are using, and again here also we are using the same thing. So this is the first example, that is the tie rod. Then second, the tension link in the bridge structure. Now even if you see here it is, this is the tension member, and here the joint we are using here, and again here we are using, right? So this is the fork end, this is the eye end, and there you are using the cotter pin. So this is the second application. Then the third one we had seen, that is the link of the roller chain. Now again if you see here, so this is the fork end outside and this is the eye end inside, and there we are inserting this the pin. So the tensile force here and here, you are getting the same application, that is in case of the link chain which you are using in the bicycle. Then the tie rod in the jib crane, right? So if you see here it is that we are using. So this is the fork end, the eye end, and with the help of this pin we are joining. Again here we are using the same joint, and the same crane here we are using in the application, right? So here that the knuckle joint, and here again knuckle joint. So these are the few applications where we are using the knuckle joint. In case of the tractor also we are using this knuckle joint. If you recall, see here it is. So this is the one end, this is the fork end, here it is the eye end, and we are joining with the help of the pin. Or even you can see here, this is the fork end, this is the eye end, and you are inserting the pin. When you connect the application here, you can easily lift. So here we are using, and again here we are using. So these are the few applications where we are using the knuckle joint. So this is what one of the example of the knuckle joint when you design and when you analyze. Now with the help of the software, it becomes very easy to analyze. So in this way you can find out with the help of the software different thing. Here they have given the nodal solution, nodal displacement, where the maximum displacement it has shown. So the green color it shows the lesser value, and as you moving on the red side, so in this way it is the value it is goes on increasing. So here it is a larger the value, and here it is the lesser value, whatever the nodal solution it is there. So we can find out different stress and other different parameters with the help of the software. So this is just for the understanding purpose. Now just now I had said that it is having the three major component. One is the eye end, second is the fork end, and the third one is the pin, right? So this is the first, this is the second, and this is the third. These are the three things which we have to design. Already we had seen in case of the quarter joint, there are again the three part, and all on these three parts we found out or we designed by considering whether the tensile stress is on there, or the compressive, or the crushing you can say, or the shear stress, and we have to check all this and we have to design based on this. Now again the force balancing, as we are applying the force P towards the left hand side, so it should be balanced. So the two ends are there, so half load will be divided here and again half here. So P by 2, P by 2, and here the P will get in this direction, and to balance again P by 2 which is fit here, right? So the same reaction you will get on this. So here P by 2 and P by 2, and the same in case of the eye end, equal and opposite here, right hand side towards the right, and there should be left hand side the force balancing. So this is the force balancing in case of the fork end, in case of the pin, or one in case of the eye end. Now we will calculate all the dimensions. So the first we will consider the tensile failure of the rod, right? So as each rod which is subjected to the tensile force P, and we will find out what is the corresponding stress induced in that. We know that the stress sigma T is equal to sigma E is equal to what it is, the load upon the area we know. And what is the area? Area which is resisting to the deformation. So as there is a circular rod, then we know that area it is pi by 4 d square. So therefore tensile stress sigma T is equal to load upon area. We had written, and if you rearrange this, then you will get the diameter of the rod is equal to under root 4p divided by pi sigma T. Then we will find out the enlarged diameter, that is the D1 we can say, near to the rod. So that we are finding out from the empirical relation, which it is equal to capital D1 is equal to 1.1 times the diameter of the rod D, which we calculated in the previous step. So by using this you can find out the enlarged diameter D1. Now next we will now consider the eye end And in this I end, we will consider all three types of the failure, whether it is tensile failure, crushing failure, and the shear failure. Right. So as there is a tensile force, so this it will fail here, and whatever the hatching part you are seeing here, so this is the area which it is resisting to the tensile failure. Now its outside diameter, it is the DO you will get, and the inside, so this is the diameter, right? So if you see, right, so the same thing here you have shown, this is isometric view and this is the top view. So inside diameter it is D. So this area we have to find out. Now what is the area you will get? This is the outside diameter DO, inside diameter D, that you will get this thickness, and if you multiply it, that is the constant, I think it is B. So DO minus D into B, you will get the area which it is adjusting to the tensile failure. So that we will see tensile failure is equal to, so this is the colored area, so that is the area which it is adjusting to the tensile failure. The same thing here you have enlarged. So therefore the area which it is adjusting to the failure is equal to DO minus D. So this is the outside diameter DO, inside diameter D. So this area will get this length, and this if you multiply by height, then you will get the area, so that is the B. Then the corresponding tensile stress sigma T is equal to load upon area, and we will put this value of area which it is resistant to the failure, we will put, then you will get sigma T is equal to P divided by B in bracket DO minus D. So this is what the first we consider the tensile failure. Now we will consider the next, the shear failure of this the I end. Now see, previous case due to the tensile, here it failed, right? So that area we have calculated. Now as this is failing due to the shear, so there is inside here there is a pin which applies the force in this direction. So here the shearing it occurs. So again there are the two areas, here one area and here it is the another area. The same thing here it is shown, the two area which it is resisting to the failure. Now we have to find out the area. How to find out this area? This is again, see, it is this thing we have to calculate, that is nothing but it is this thickness. So if I calculate this DO minus D, then this thickness and this thickness you will get. If I take divided by 2, then you will get this. So approximately you will get this thickness is equal to this DO minus D divided by 2. So this thickness you will get. And as there is a 2 area at the upper side and the bottom side, so there is a double shear, so we have to take the 2. So therefore we will get the A1 area, that is DO minus D divided by 2 into B. If I take this width, that is B, it is there, right? So this is the one area, and as there is a double shear, so we will multiply it by 2, the same area. So we will get the area, this 2 it will get cancelled, then again I will get the total shearing area is equal to DO minus D into B. Now we can find out the corresponding shear stress. It is in this, the tau is equal to the load upon area. We know that is the tau is equal to load upon area, the area which it is resisting to the shear failure. That now we calculated this, that we will put here in the area. Therefore, we will get the tau is equal to P divided by DO minus D into B. So this is what the shear failure. And the last, in case of this I end, that is the crushing failure of this I end. Now what happens, as this is the pin which it will exert the compressive force on that the I end. So if I consider here, it is the another the outside area, and this is the pin which it is applying this compressive force. So this area inside this pin, right? So where you are getting compressive. So this is the area which I had shown shaded area, which it is resisting the crushing failure. Now that we can calculate. So this is what the diameter small d, and this is the width B. So B into D will get the area. So this is the shaded area which resists to the crushing failure. So therefore the crushing area is equal to B into D, then sigma C is equal to load upon area, and area is nothing but B into D. So this is what we considered the I end, on which the tensile stress, shear stress and the crushing stress, all these three types of the failure of the stress we considered. That is what the design related to the I end. Now we will move to the next, the fork end. Again here we have to consider all these three. Out of that, the first will consider the tensile stress. Now when there is a tensile load acting on this, again I will show you this one, and here it will fail. So or you want to see here when there is a tensile load, here you are applying the load P, and again here inside there is P by 2, and somewhere here the failure it occurs, right? So the resisting area here at the top 1, and here at the bottom 2, and this is the 3, and here it is the 4. So these are the area which are resisting to the tensile failure that we have to consider. So the same thing here I had shown, right? So this green color, it shows the area which it is resisting to the tensile failure. Now what are the dimension? We know that the outside diameter, it is DO. Here in the side figure you will come to know. Outside diameter, this is the DO, and inside diameter it is D. So DO minus D into A, if I take, then you will get the one area, right? So DO minus D, so this one and this one, you will get the area, and again at the upper side also, if you multiply by 2, or DO minus D divided by 2, then you will get the one area, and multiply by 4, as there are the 4 area, so that is the resisting area you can calculate. Now the same thing, twice DO minus D, this is the total area you will get. Now I hope you understand. Once I will repeat, this is the outside diameter DO, inside diameter D means this thickness and this thickness you will get, and if you multiply it by A, then you will get this bottom area which is hashed in the red color, and again at the upper side, so therefore twice A DO minus D. So this is the total area which it is resisting to the tensile failure. Now we can find out the tensile stress. Sigma T is equal to load upon area. Area just now we calculated. This value we will put in this equation. So sigma T is equal to P upon twice A in bracket DO minus D. So this is what the tensile failure of the fork end. Now we'll see the shear failure of the fork end. Now again we will see the figure, you will come to know here. Just now here it is the tensile. Right. So whenever there is a force, so here the shearing, as there is a pin inside this, due to that it may shear off, right? So this part it will come outside. Similarly again here it will get a shear off, right? So this is the shearing area here, here, and here. The two forks are there, two ends are there of this fork. So here again the shearing two side, here again the shearing the two side. So where you will get the shear failure. So that we'll see here. So this is the area where the shearing at the top and shearing at the bottom. So this green color area. So again there are the double shear at the top and double shear at the bottom. So this is one area here, if you see here. So this is the second area. So this is the third, and here again this is the fourth. Here at the back side you are not seeing right now, but here whatever the green area you are seeing, the similar here on the other side. So the four areas are there. So that we will see. Now see here, it is shown here and here. The same thing here, this area, and this one is the here. So you will come to know right now. Then again this thickness you have to find out what it is, as this is the diameter DO. So DO minus this D, then you will get this thickness and this. So DO minus D divided by 2, then you will get this thickness, right? So this is the 1, and again this is the 1. So if you multiply it by 2, then you will get this here area which it is resisting at the top side. Again same at the bottom side, then again you have to multiply it by 2. So that we will see here. Then you can find out DO minus D divided by 2 into A. This is the 1, and as there are the 4 different shear planes, 1, this is 2, and here at the back side 3, and here it is the 4, then I will multiply it by 4. So 4 d1 minus divided by 2 into A. So therefore we will get A is equal to twice d1 minus d. So this is the area which is resisting to the shear failure. Now again we will put in the equation the shear stress tau is equal to load upon the area, and we will put this area, we will get the equation tau is equal to P divided by twice A d1 minus d. So this is what considering the shear failure of the fork end. Now the next, it is the crushing failure of that fork end. So here you are getting the crushing, that is the compressive force on this. So there is a compressive stress acting on this. So this is the area which comes under the crushing. This area we have to consider. Right, so this is what the pin, inside there is a pin which it is applying the compressive force. So this is the area. So this diameter is D, and this thickness you are getting as A. So A into D, this is the bottom area, and again at the top A into D. So twice A into D, this is what the area which is resisting to the crushing. So here this one A into D, and again this one A into D. So therefore twice A into D, we will get the crushing area. Therefore crushing stress sigma C is equal to load upon area. So we will put the, here it is sigma C, right? So P upon twice A into D. So this is the crushing failure of the fork end. Now we will design the pin which is under the shear. So as there is a pin, due to that it will fail the shear. Here it is the one area, and here it is another area. So the junction between this upper part is in the fork, and this is the eye. So here it will shearing takes place. Again here it is the eye and the fork junction. Here the shear it will takes place. So as this is the circular pin, then we will get the pi by 4 d square, that is the area, and there is a double shear. So twice pi by 4 d square we will get. So the twice double shear, it is at the top and the bottom, and the area of this circular pi by 4 d square. So therefore the crushing stress induced in this pin tau is equal to load upon the area just now we found out, then P divided by twice pi by 4 d square. So this is the shear failure of this pin, and that we will find out either the shear stress or the reverse dimension of that pin. Now when the pin is new, at that time only shearing it may take place, but after some usage of this component due to decay and the corrosion erosion, the component it may fail due to the bending also. That we will consider here. So before that, the crushing also we will see. So this is the pin on which the compressive stress you are getting, the compressive load, and this pin may be under compression. So this is the area resisting, that is this length of the pin inside that the eye end, and this is the diameter. So its view here. So the perpendicular area we always take. So this is the area, actually this is the area, but the perpendicular area if I take section here, so this you will get. So L into D you will get. Therefore the crushing stress is equal to force upon area, therefore the load P is equal to L into D. So you will get. So the L may be the length of this pin here inside this the eye end. As we had seen that length is A, we can take A here, and that is what you can take A into D also you can take. So that is the crushing failure of this pin. Now the bending failure of the pin we will take. So we know here the bending moment is maximum at the center, similar case which we had seen in case of the quarter pin. Already we understood that. So the maximum bending moment is at center, so we will take bending moment at the center, and whatever the forces towards left hand side are there, by considering that we are taking the moment. So again the same the assumption which we have seen quarter pin, that the forces in the eye end, that is uniformly distributed, and the forces in the fork end on the pin, that are uniformly varying from 0 to maximum. So this is the assumption which already we are aware about that. Now as we are taking section here, maximum bending moment is here, so that the force, so this is uniformly distributed load, this is the P, and if I take the section here, so on the left hand side this P, so that will get the P by 2, which will act at the center. So same thing here we are applying, and this uniformly varying load, it is P by 2, and the same thing, this P by 2 we are applying here. From this end it is 1/3 of this total distance A. So there are the two forces on the left hand side, and we will take moment here at this axis. So this distance x is what, this if I assume it as a x, so it is from the higher end, so 1/3 we are taking. If from the lower end, it is 2/3 of the distance. So this 1/3 of this distance A, that is 1/3 of A, you will get this distance, and this distance Z, it is there. What is the Z? So from center here to this distance. So initially it is B, and the half distance it is B by 2, and again Z is what, half of that B by 2. So therefore we will get 1 by 2, that 1 by 2 B. So we will get B by 4. This is the Z. So we know the distance Z and the X. Now we can take the bending moment here at the center. Now there are two forces. This is P by 2 and upward direction, and this is P by 2 in downward direction. Now this P by 2, it is rotating in this direction, that is the clockwise direction. This distance we have to take when we are taking moment. So this is B by 2 and this is the plus X. So P by 2 into B by 2 plus this X. So that is what the moment in the clockwise direction. Then the second one force, this it is rotating in anti-clockwise direction. So therefore I will take minus this P by 2 into this is the Z. Now already we calculated this X and Z that we will put in this equation, and we will get this P by 2, B by 3, it is X is equal to what, A by 3 will get, and P by 2, this Z is equal to B by 4, which already we calculated. Now P by 2 is common, that we will take outside, and then we will get this equation, and again B by 4, B by 2 here, we can add these two. If I multiply it by 2 by 2, then 2B by 4 and B by 4 minus, so we will get B by 4 plus A by 3. Now this is the bending moment we will get. Then the moment of inertia of this I we can call as this is the circular section. Then we will get pi by 64 d raised to 4, which already we are aware. And then Y is what, the distance from this neutral axis to the outermost layer, it is d by 2 we will get. So now we can find out the bending stress induced in the pin is equal to bending moment divided by moment of inertia into Y. Now already we calculated the bending moment, what it is, the moment of inertia and the Y. Now we will put all these three equation here in this, then we will get this equation. Therefore if you rearrange this, we can say that the bending stress sigma B is equal to 32 divided by pi d cube into P by 2 into in bracket B by 4 plus A by 3 bracket complete. So this is what the bending stress induced in this the pin. That will. Okay, thank you. We will see next thing in the next lecture.